Welcome back to The Explainer. Today we're diving into something that's absolutely foundational to our modern world, the evolution of computer languages. We're going to trace this incredible journey from raw, primitive binary, literally just ones and zeros, all the way up to the sophisticated, high-level code that powers basically everything we use today. If you've ever wondered how we actually bridge the gap to command these machines to perform highly complex tasks, well, you are absolutely in the right place. We're going to break the whole thing down step by step. So, to kick things off, I want you to consider this core question. How do we actually communicate with computers? Think about it. We interact with smartphones, laptops, and servers all day, every single day, right? We tap, we type, we swipe, and the machine just instantly responds. But here's the thing. Computers don't natively speak our language. They don't understand English or Spanish or natural voice commands right out of the box. So how exactly do we cross that massive divide? You know, humans have these incredibly rich, nuanced languages, and even animals communicate through pretty complex systems of sounds and physical signals. But a computer, it sits completely outside the biological realm. It literally can't interpret human words naturally, nor can it read biological signals. It requires a fundamentally different approach if we want it to understand us and actually execute what we need it to do. All right, so here is our roadmap for today's explainer. First, we'll look at how computers actually listen. Then, low-level languages, or speaking in binary. Third, high-level languages, the human bridge. Fourth, we'll do a high versus low-level comparison. And finally, number 5, essential vocabulary and a look into the future. Section 1, how computers actually listen, and the inherent communication gap between humans and machines. Okay, let's dive into this. To cross this huge communication gap, we invented computer languages. And really, these are just highly specific instruction sets designed to make human-computer interaction possible. We specifically engineered these formalized languages so that we, the humans, can write the logic, set the precise parameters, and then just let the machine do all the heavy lifting. It executes these incredibly complex tasks at a speed we could literally never match manually. Moving on to Section 2, low-level, speaking in binary, interacting directly with computer hardware. Now, what's really interesting about this concept is that the foundation of all computing essentially just comes down to digital electronics, and that operates entirely on the presence or the absence of electrical voltage. So using positive logic, the presence of voltage is a 1, and the absence is a 0, or, vice versa if you're using negative logic. A system only uses one of these rules at a time. The machine reads these physical voltage states directly. This raw, immediate hardware communication, that's machine language. It is completely stripped of any human abstraction, just ones and zeros. But as you can imagine, staring at endless strings of ones and zeros is pretty brutal for developers to manage. So assembly language became our first real shortcut. By using symbols, often called mnemonics, to represent addresses and data, it gave us these human-readable shortcuts. However, because we kind of abstracted slightly away from the raw hardware, this approach actually requires an assembler to translate those symbols back down into the raw binary machine code. Which brings us to Section 3, high level, the human bridge, making programming intuitive and error-free. So, when we move up the evolutionary ladder and abstract away the hardware management entirely, we get high-level languages. I'm sure you've heard of some of these: C, C++, Java, JavaScript, Python, C#, PHP. By relying on English-like keywords and standard mathematical symbols, developers can focus purely on the logic and architecture rather than stressing over managing raw voltage states. This abstraction is a total game changer. It drastically reduces coding errors and makes everything so much more intuitive. Section 4, high versus low level, a head-to-head comparison. So the crucial point here is that in computer science, everything is a trade-off. Let's break it down. High-level languages give you incredible human readability, they're super friendly for programmers, they're easy to debug, and they're highly portable across different systems. But you pay a tax in execution time because of those required translation layers. On the flip side, low-level languages offer blisteringly fast execution and absolute, uncompromised hardware control. But they sacrifice portability and ease of use, tying you directly to a specific piece of hardware. Yet even with these massive operational differences, we have to remember they share the same fundamental DNA. Both require strict logical steps and flow. Both utilize powerful control structures like loops and conditionals, and both ultimately demand some form of translation, whether that's a compiler or an assembler, down to the machine level to actually execute tasks. They're basically just different tools bridging the exact same gap. Let's move to Section 5 and see how this all builds together. Essential vocabulary and the future. To truly understand the language of code, we need to know the foundational building blocks. First up, a statement. Now, a statement isn't just some generic action, it's literally the atomic unit of logic in any program. It's the absolute baseline command telling the computer how to do a desired action using specific words or instructions. Now, if statements are the atomic vocabulary, then syntax is the strict, unforgiving grammar. The machine leaves zero room for interpretation here. Syntax is the structured arrangement of those statements. And trust me, if you break the syntax, the entire compilation process just halts. Then we have the algorithm. Far beyond just being a trendy tech buzzword, an algorithm is a specific set of instructions written to solve a problem. Think of it as the pure, logical thought process of a computer, structured step by step to arrive at a highly efficient solution. And underneath all of those elegant, algorithmic architectures is the binary number. It's simply a way of expressing data using only the numbers 1 and 0. No matter how incredibly advanced your high-level language is, ones and zeros remain the inescapable bottom line. It's the only language computers actually understand at the hardware level. So coding, therefore, isn't just typing commands on a screen. It's the deliberate process of creating these computer instructions, also known as programs. It's the active synthesis of those atomic statements, bound by strict syntax, shaped into algorithms, and translated into a format the physical machine can rapidly execute. We've traced this incredible evolution from raw hardware voltage all the way to the elegant high-level abstractions that literally run our modern world. It's an amazing trajectory of human ingenuity. But as artificial intelligence begins to actively write, debug, and optimize its own code, we really have to ask a profound question. Are human-readable programming languages just a temporary bridge in the grand history of computing? What will the next generation of computer languages even look like? Keep exploring, keep questioning, and I'll catch you in the next explainer.